The second theorem which we are going to discuss today is called the final value theorem. Okay. Suppose that capital F is continuous on the interval 0 to infinity and is of exponential order alpha, and F prime, that is the derivative of F with respect to t, is piecewise continuous on the interval 0 to infinity. And furthermore, limit f of t when t tends to infinity exists. If this limit exists, then the value of this limit f of t tends to infinity, should be equal to limit small s f of s, small f of s, that is s times the Laplace transform of f of t in the limit s tends to 0. If the left hand limit exists, then it should be equal to this right hand limit. So when t tends to infinity, s tends to 0. And here, when t tends to 0, s tends to infinity. Okay. So let us look at one exception for this. Segi function segi exception nama yang here, let us take the function f of t equal to sine t. Let us take this function. Then what is the Laplace transform of sine t? The Laplace transform of sine t is s divided by s squared plus 1. And when we take the limit, s tends to 0. What do we get? When we take the limit, s tends to 0, this simply becomes 0 because the numerator is 0 and the denominator is 1 in the limit s tends to 0. So the limit is 0. This limit is 0. But limit of sine t when t tends to infinity, this limit does not exist because sine t keeps oscillating between -1 and +1. Okay, it does not converge to any number when t tends to infinity. It keeps on oscillating between -1 and +1. So limit t tends to infinity, sine t does not exist. Okay, so since it does not exist, we should not equate this limit with this limit. Okay, I repeat, since this limit does not exist, we should not try to equate the limit. Let me draw it here. Since this limit does not exist, we should not try to equate this limit with this limit. Limit anisi mana dev. These two limits are not the same. We should not try to equate them because limit sine t does not exist. Okay. Okay, fine. Now let us look at another example. Find limit of capital F when t tends to 0 from the right and limit of capital F when t tends to infinity if the Laplace transform of the function is given. That is 1 by s plus tan inverse a by s. Okay. So we use the two limiting theorems. Okay. So from the first theorem, we know limit f of t tends to 0 from the right. This is equal to limit s tends to infinity s times the Laplace transform of f. So this is limit s tends to infinity s times the Laplace transform of s. This is the Laplace transform of s. And if I multiply this by s, I get 1 plus s times tan inverse a by s. So 1 plus tan inverse a by s. So we can open the bracket now. So limit s tends to infinity 1, it will remain 1. Then limit s tends to infinity, tan inverse a by s times s. So if we look at this, this becomes, when s tends to infinity, this s will tend to infinity, and this s will tend to infinity. So this becomes tan inverse a by infinity, that is 0. So this is of the form infinity times 0. Okay. So this is of the indeterminate form, infinity times 0. So what do? We bring s in the denominator. Okay, we bring s in the denominator. Okay, so we get tan inverse a by s divided by 1 by s. Okay, Now this becomes 0 by 0 form. Okay, so this is in the limit s tends to infinity. This is of the indeterminate form 0 by 0. Okay, now to find this limit, we can apply the L'Hopital rule. It is written as L'Hospital's rule, but it is read as L'Hopital's rule. So let us apply L'Hopital's rule. And what does L'Hopital's rule say? You differentiate the numerator with respect to s. You also differentiate the denominator with respect to s, and then you apply the limit. Okay, so we differentiate the numerator with respect to s, we get this expression. If we differentiate the denominator with respect to s, I get -1 by s square. This s square and s square, they get cancelled out. So now I apply the limit s tends to infinity. So in the limit s tends to infinity, this this becomes 0. This becomes 0, and I am left with minus a here in the numerator and -1 in the denominator. So it becomes plus a. So I get 1 plus a. So this is the final answer. Okay. Now let us find the other limit. That is when t tends to infinity. So at limit f of t when t tends to infinity. This is limit s of fs when s tends to 0. And we have seen that s times fs is this 1 plus s times t inverse a by s. So this is limit s tends to 0, 1 plus s times t inverse a by s. So in the limit s tends to 0, this becomes 0, and tan inverse a by 0 is infinity. So tan inverse infinity is pi by 2. So this becomes 0 times pi by 2. So it becomes 0 times pi by 2. And 0 times pi by 2 is 0. So the final answer that we obtain is 1. Okay, 1. So this is how we can calculate the limit of a function by using the method of Laplace transforms. Okay. Now let us look at the Laplace transform of this wave form, periodic half sine wave. Find the Laplace transform of the periodic half sine wave. Okay. This can be the output of a half wave rectifier. I repeat, this can be the output of a half wave rectifier. Fine. So this function is a periodic function with period capital T. Okay. So how can I write it here? Okay, that is fine. This is a periodic function with period capital T. Okay, that means after a time interval of capital T, the function repeats itself. Okay, in the first half period, the function is given by a sine curve. In the second half period, the function is 0. I repeat, in the first half period, the function is a upper sine curve. In the second half, it is 0. Okay, so how do we proceed? This we can find by using a result which we had obtained earlier. We had obtained earlier that the Laplace transform of the first period was shown to be this. That is the Laplace transform of the first period. In an earlier class, we had calculated the Laplace transform of this single sine wave. I repeat, in our earlier class, we had calculated the Laplace transform of this single sine wave, and it turned out to be this expression. This was the expression which we had obtained earlier. This was the Laplace transform for this single sine wave. Okay, and it was given by this expression. That is fine. Now what remains to be done is simply to apply our formula for periodic function. Okay, and the formula for periodic function is Laplace transform of capital F of t. This is equal to 1 divided by 1 minus e to the power minus s times the period Here the period is capital T times the integral of the function from 0 to t. The integral of the function from 0 to t. Okay, and that integral of the function from 0 to t, if we consider only this single sign, if we consider only this single sine wave, the integral from 0 to t is equal to the integral from 0 to infinity. I repeat, if we consider only the single sine wave, the integral from 0 to t is equal to the integral from 0 to infinity, and that is simply equal to the Laplace transform of the single sine wave. Okay, so the Laplace transform of the single sine wave is this. So we simply substitute it here. Okay, so this particular example is how to calculate the Laplace transform of the output of a half wave rectifier by using the formula for periodic function. We can take the output of a full wave rectifier also. If it is the output of a full wave rectifier, then the output would be something like this. The output would be something like this. So this is again a periodic function with period t by 2. Okay, so the output of a full wave rectifier would be something like this. So this is again a periodic function with period t by 2. So the answer would be the same, except that this period here, this period will change to t by 2. Instead of s minus st, this will change to s of t by 2. Okay, so this particular t will become t by 2. Right? So you try this as your homework to find the Laplace transform of the output of a full wave rectifier. Okay, this is fine. Let me clear all the drawings. Okay, this is fine. Let us look at another example. I think this will be the last example for today. This will be the last example for today. This is how to solve differential equations. I repeat, how to solve differential equations or integral equations. This is an integral equation. So how to solve integral equations by using the method of Laplace transform. So solve the equation r times it plus 1 by c integral I dt from 0 to t. This is equal to capital ET, where capital ET is shown in figure and ET is given by this graph. That is, ET is equal to E0 from 0 to A, for values of t from 0 to A, and then from A to twice A it is 0, then from twice A to thrice A it is equal to E0 again, then from thrice A to 4A it is 0, and so on. This can be written, this function can be written in terms of unit step function. I repeat, this graph, this is the graph of the function E of t. This can be written in terms of the unit step function, and it is given by this expression. It is given by this particular expression. Okay. This E of t, whose graph is given here, the function the E of t is given by this expression. Okay, you try it as your homework to prove that the graph of this function is equal to this graph. Fine. So the graph of this function is equal to this graph. You try to prove it as your homework. So this integral equation, this above equation, it expresses the current flowing through an RC circuit as shown in the figure. So it is the current flowing in this RC circuit where a resistor and a capacitor are connected in series, and a source, a voltage source, is applied to the series circuit. Okay, so this is the expression given by Kirchhoff's loop rule. Okay, Kirchhoff's law. This is the formula given by the Kirchhoff's loop law. Okay. So let me clear all drawings. So this function e of t is given by this expression. Okay, that is fine. Now let us take the Laplace transform of this equation. This given equation, when I take the Laplace transform, this R is the value of the resistance and it is a constant. This C is the value of the capacitor, it is also a constant. So here R is a constant, C is a constant. So when I take the Laplace transform, R is a constant, it will not change, C will not change. The Laplace transform of small I becomes capital I. The Laplace transform of this integral, it becomes I by S. And since we have a C here, so it becomes capital I by CS, and Laplace transform of E of t. And the Laplace transform of E of t. And what is E of t? E is E0. E0 is a constant, so it can be taken outside. And what is the Laplace transform of U of t? U of t is 1 by S. Laplace transform of U of t minus A. This is e to the power minus as by s. So this is what we have seen in our shifting theorem. So this shifting theorem this we have simply applied the second shifting theorem here. Okay, this is the second shifting theorem. So using the second shifting theorem, we get the Laplace transform of E is given by this expression. Here capital I is the Laplace transform of small I, and I is the current. Small I is the current flowing in the circuit. So what are we going to find out here? We are going to find out the current which is flowing in the circuit. We are asked to find out the current flowing in the circuit when the external applied voltage is this rectangular waveform. Okay. So I combine these two. I take IS common, R times IS common, R times IS common log to A. So it becomes 1 plus 1 by SRC plus E0 by, I can take 1 by S common from here. So E0 by S, 1 minus e to the power minus AS plus e to the power minus twice AS and so on. Okay. After that, what I have done is I have simply simplified this expression in this form, and I have left others unchanged. So CG forms is the spine Ibudanika. Then I take this term towards the right, and also divide by R. So E naught becomes E naught divided by R, and I have a factor 1 by S here. Then this becomes SRC divided by 1 plus SRC. Okay, so this S, it cancels with this S. All other terms remain unchanged. This I can write as E naught by R in the numerator. Then I divide both numerator and denominator here by RC. So this becomes 1. This becomes 1 by RC. We have 1 by RC here, and this becomes S. So I have E naught by R divided by S plus 1 by RC, and this term inside the bracket, it remains unchanged. So this is capital IS. Now, if I want to find the current now, what should I do? I should take the inverse Laplace transform. Therefore, we obtain the current flowing in the circuit by taking the inverse Laplace transform. So small I of t is equal to E naught by R, that is a constant. E naught by R, that is a constant. This S plus 1 by RC, I take it inside the bracket and divide each term by S plus 1 by RC. So inverse Laplace transform of 1 divided by S plus 1 by RC minus inverse Laplace transform of e to the power minus AS by S plus 1 by RC, and so on. Okay. Then inverse Laplace transform of 1 by S plus 1 by RC. If we apply the first shifting theorem, okay, if we apply the first shifting theorem, that is S shifting. If we apply the first shifting theorem, this becomes e to the power minus 1 by RCT. Okay, I get this expression by applying the first shifting theorem. Okay, here in we are going to apply the first shifting theorem as well as second shifting theorem. So first we apply the first shifting theorem, and according to the first shifting theorem, this becomes e to the power minus 1 by RC t. And according to the second shifting theorem, t should be replaced by t minus a and u of t minus a. So I have applied the first shifting theorem and the second shifting theorem, and I get this expression. Similarly, I apply the first shifting theorem and second shifting theorem, I get these expressions. Okay, so I get this infinite series. Now, this is the current written in unit step functions as an infinite series of unit step functions. Okay, now if I want to find the current in the interval where t lies between n times a and n plus 1 times a. So what will be the value of the current in this interval, during this time interval? Okay, when t lies between n times a and n plus 1 times a, then u of t minus a definitely would be 1, u of t minus twice a definitely would be equal to 1, u of, because since t is greater than n times a, u of t minus n times a will be definitely greater than 1. But since t is less than n plus 1 times a, u of t n plus 1 times a would be 0. Okay, so in this time interval, all the other unit step functions are 0 up to u of t minus na. After that, all the unit step functions are 0. I repeat, when t lies in this interval, all the unit step functions are 1 up to u of t minus na. Up to u of t minus na, all the unit step functions are 1. After that, all unit step functions after u of t minus n plus 1a are 0. Okay, so in this expression, only those terms up to u of t minus a will survive. So this is, so this will survive up to u of t minus na will survive. So this will survive up to t minus na. Okay, so t minus na, this will survive. So it becomes, this is 1 minus, sorry, e to the power, let me reduce the size a little bit. I don't know if it will be visible to you or not. Okay, this is fine. So E naught by R, we have e to the power minus t by RC, e to the power minus t by RC. We have taken common, then this becomes 1 minus e to the power, this minus and minus, it will become plus, so a by RC. This will be plus minus and minus, this will become twice a by RC, and so on. This will continue till NA by RC. NA by RC. Okay, so fit it. So we have obtained this expression. This is for that value of t which lies between NA and n plus 1a. So when t lies in this interval, the value of the current is given by this expression. And this term inside the bracket, you can see that this is a geometric series. This is a geometric series with common ratio given by this term. Okay, this term. And how many terms are there? There are n plus 1 terms. Okay, and by using the formula for geometric series for n plus 1 term, we get current I equal to E naught by R, this e to the power minus t by RC, sum of these terms. And sum of these terms is 1 minus the common ratio. The common ratio is this, to how many terms? N plus 1 terms divided by 1 minus the common ratio. And 1 minus common ratio minus minus become plus e to the power a by RC. So this is the expression for, I repeat, this is the expression for the current. Okay, this is the expression for the current when the time lies between NA and n plus 1a. Okay, So let me pause the recording here.